Sample problem 16.3 takes our method of initial rate that we kind of practice with our in-class problems and applies it to a real reaction. And in this case, they've actually already given us the general rate law. So the general rate law is just written as rate equals rate constant times one of the reactant species raised to the n power, other reactant species raised to the n power. Again, it's the product of both of these. We're multiplying them together. And the purpose of the method of initial rates is to determine reaction orders by comparing rate data that allows us to evaluate how the rate changes as we change concentration. So to solve for M here, okay, M shows us the reaction order with respect to NO2. We need to have reactions where NO2 changes, but CO is held constant, okay? So we need reactions where NO2 changes, but CO is held constant. And unlike our in-class problems, we actually are only given 3 experiments here. So there's really only one that will work, and that's to compare 1 versus 2. So again, what we need to figure out here is how the rate changes. So the rate for reaction 2 compared to the rate for reaction 1 as a function of the change in the concentration of NO2. So we need to put in the concentration for NO2 from experiment 2 and the concentration of NO2 from experiment 1. So what we have then is 0.08 moles per liter second, 0.005 moles per liter second. And I should say that this really is raised to the m power because we're trying to figure out how these are related. So we've got the reactant concentration for reaction 2 is 0.40 moles per liter, 0.10 moles per liter, again raised to the m power. So in our sample problem, we kind of just were talking about what's the ratio of the rates compared to the ratio of the concentrations. This is looking at it with a little bit more of an equation standpoint, but really what we're doing is looking at the ratio of the rates compared to the ratio of the concentrations, and we're asking how are they related? What kind of exponent will allow us to relate these? So what we have here is a ratio of the rates, that's 16. A ratio of the concentrations, that's 4, and the only way that will allow us to relate these, and you can probably look at this and just kind of see that that's going to be a square there, but if you didn't, again, to figure out what m is, you can figure out m by taking the log of 16 over the log of 4, and that equals 2.0. So again, m is equal to 2. We could have figured that out easily just kind of looking at this, but if you can't figure out the math easy in your head, to figure out what m is, okay, you take the log of the first term and divide it by the log of the term that's with that m. So the log of 16 over the log of 4, that will give you 2. So that we can say that this is second order in NO2. So again, same kind of a treatment to solve for N. We need reactions where CO changes, but NO2 is held constant. So 1 versus 3 will do that for us. So comparing the rate for reaction 3, the rate for reaction 1, and we're asking how concentration of CO changes from reaction 3 to CO for reaction 1. And we're going to figure out N by looking at how those ratios compare. So putting in the data here, 0.005 moles per liter second, 0.05 moles per liter second, 0.2 moles per liter, 0.1 moles per liter, N. And maybe you could actually look at this and see it just from the table here. Comparing 1 to 3, right? We can see that we've doubled the concentration of CO, but it hasn't changed the rate. The only way that can happen is if the reaction is 0 order with respect to CO. But let's actually go ahead and take this and we can figure out what mathematically we'd get when we'll see that we do get 0. So we get 1 equals 2 to the n. And maybe you already know this. The only way to have any number be raised to an exponent and have it be equal 1 is if n is 0. But again, using our equation here to figure out what n is going to then be equal to the log of 1, so the term on the left, over the log of 2. And the log of 1, right, is 0. So it doesn't even matter what the log of 2 is. The log of any number raised to the 0 power will equal 1. So n is equal to 0 here. So we are 0 order with respect to NO2. Okay? So writing our, let's see, this just, I think the problem just asks us to figure out individual and overall reaction orders. So it's second order, whoops, and I wrote this wrong here, second order with respect to NO2. This is actually 0 order with respect to CO. So it's second order with respect to NO2, 0 order with respect to CO. And if we were to write our rate law, rate equals rate constant times NO2 squared, and CO does not appear in our rate law because the reaction is 0 order with respect to CO. And just as a highlight, remember we saw in a previous problem, that does not mean that carbon monoxide is not necessary for this reaction. It just means that its concentration will not affect the rate. And as we'll see as we move on in some later portions of this chapter, what that really means is that carbon monoxide is not part of the slow step of the reaction. The slow step of the reaction actually only involves NO2 molecules.